Last video, we talked about Boolean values and propositions. This video, we want to extend our ideas of propositions by looking at connected simple propositions, and which are also propositions. We connect them using Boolean operators. So in this video, we want to talk about our Boolean operators. So, logical statements can be simple propositions, as the ones we talked about during the last lecture, or they can be formed from operations on simple statements or propositions. In other words, they could be functions of propositions. These operations are known as Boolean operators, and the outputs are true, false. So, propositions. Let's just give an overview of the types of Boolean operators we're going to be looking at. The name, sort of the meaning, and I have indicated the symbol used. So the first Boolean operator we're going to investigate is negation, or not. Then we'll look at conjunction, which joins two propositions with the English word and. We'll look at the operator disjunction, which connects using or. We'll look at implications. It means implies. So if one proposition implies another proposition, it's an implication. Often in English, these are identified by if, then, and an arrow is used to indicate it. It could be an arrow where it's pointing in from left to right or from right to left. It means that the arrowed part is the one that's implied. The proposition with the arrow is the implied proposition. And then we have equivalence, which is going to be very important to us. It means if and only if. Sometimes we say equivalent to, and we use a double arrow in this particular case. So what I intend to do is to look at each one of these Boolean operations separately and give you some examples of their use. So to start with, though, I wanted to look at a simple proposition like in the last video. Say 5 is positive. Now one of the things we'd like to do is to be able to write this symbolically. 5 is positive. So we could write that as 5 is greater than 0. That's 5 is positive. And notice that this simple proposition is true. The number 5 is greater than 0. So now let's investigate some of the Boolean operators. We first looked at negation, not. An example using our simple predicate of negation applied to it is 5 is not positive. We could write that symbolically as it is not the case that 5 is greater than 0. Of course, we also know we could write that as 5 is less than or equal to 0. But symbolically, in form of a proposition, not 5 is greater than 0 is a proposition that is always false, because 5 is greater than 0. So this is false, or evaluated to false. For general propositions, when we apply not to it, if the proposition is originally true, not that proposition is false. When it's false, not that proposition is true. So this is one of our simplest Boolean operators. The input is one proposition and the output is a proposition. In next videos, we'll talk about predicates, and actually these operators apply to predicates also, which are extensions to propositions. More details later. So the next Boolean operator I wanted to talk about is conjunction. 5 is positive and 6 is positive is an example. Now symbolically, I could write this as 5 is greater than 0 and 6 is greater than 0. Or if I think of 5 as being the proposition P, 5 is positive as proposition P, and 6 is positive as proposition Q, then I'm symbolically looking at P and Q. Now, in this particular case, 5 is positive and 6 is also positive, so this proposition is true. In general, for a conjunction to be true, both of its, I'm going to call them components, the simpler propositions, must be true. So if a conjunction is true, the inputs both must be true. It's a little more complicated because we're inputting two propositions and the output is a proposition. Disjunction is the next Boolean operator I want to look at. If we have 5 is positive or 6 is positive, we can connect the propositions with the operator or the disjunction. So symbolically, we could write this as 5 is greater than 0 or 6 is greater than 0. If I think of 5 is positive as the proposition P, 6 is positive as the proposition Q, I could write this as P or Q. And in this case, the truth value is true because both 5 is greater than 0 and 6 is greater than 0, and this or includes the possibility that both are true. In order for a disjunction of logical expressions to be true, at least one of the components must be true. So either P is true or Q is true. And in this case, it's both, so the result will be true. Let's look at another Boolean operator. If 5 is non-negative, then 6 is positive. That's an implication. We could write this as 5 being greater than or equal to 0. Non-negative means not negative, which means greater than or equal to 0, because it could be 0. Implies that 6 is positive, is greater than 0. And again, if this is P and this is Q, then I could write this as P implies Q. Notice when I read this, I said non-negative means greater than or equal to 0. So I actually could have rewritten this expression, this component as 5 is greater than 0 or 5 is equal to 0 implies that 6 is greater than 0. Okay, now when I'm trying to determine whether the result of the implication operator is true or false, it turns out that as long as P in general is false, the expression is going to be true. If P is true, then Q must be true for the expression to be true. In other words, the only time that an implication is false is if P is true, but Q is false. It's like a promise. If I say, if you do well on an assignment, then you can treat yourself to an ice cream. Well, the only time we get into trouble is if you do well on the assignment and you don't get the ice cream. So as long as you don't do well on the assignment, whether or not you got the ice cream doesn't make the promise not hold. So, in other words, when you have an implication, the only time an implication is false is if P is true and Q is false. So, the last of the Boolean operators I want to talk about is the equivalence. We're going to be using this a lot to prove our program's correct. But the idea here is it's an if and only if. So 5 is non-negative if and only if 6 is positive. We could write symbolically as 5 is greater than or equal to 0 if and only if 6 is greater than 0. Now, again, if I think of this first component as being P and the second component as being Q, we could write this as P is equivalent to Q. Another way of expressing this same Boolean operator is it's actually a combination of two. That's where the if and only if comes in. For P to be equivalent to Q, it must be the case that P implies Q and Q implies P. So it's actually a combination of two Boolean operators that we've observed before that gives us this equivalence. Notice that the only way an equivalence is true is if both P and Q have the same truth value. So P being true and Q being true, true implying true is going to be true, true implying true is going to be true, so the expression is going to be true. If they're both false, it's still okay, because this expression will be true and this expression will be true if they're both false. But let's say P is true and Q is false. You'd have true implying a false, which is going to be false. False in anything is false. So it has to be the case that that P and Q, both propositions, have the same truth value if the equivalence holds. And I say holds meaning gives the value true. So these were the Boolean operators applied to propositions. We're going to extend our ideas of logical expressions to those that might involve variables in the next video.